Hello children, let's look at a few properties from the chapter of circles. The first property that we are looking at is if two chords of a circle are equal, then their corresponding arcs are congruent. And conversely, if the arcs are congruent, then their corresponding chords are equal. What do we mean by that? Suppose if this is your circle and we have any two chords equal, say let us call the two chords as say chord AB is one of the chords and we have another chord say BC. These two chords are equal. Okay. Which is the arc corresponding to the chord AB? The arc corresponding to chord AB would be this arc, and the arc corresponding to BC will be this arc. Now, what we understand from here that if the chords are equal, then the arcs are also equal, then the corresponding arcs are equal, and vice versa, or conversely, if we have any two chords, we don't know whether they are congruent. We have any two chords. Again, let us call the chords as AB and CD, BC. Okay, we're looking at chord AB and chord BC. You could have taken it anywhere. If their arcs are congruent. Now, what are we saying? If their arcs are congruent. That means if arc AB, if arc AB is congruent to arc BC. If these two arcs are equal, then their corresponding chords, which is the chord corresponding to arc AB, definitely chord AB, and the chord corresponding to the arc BC, chord BC. If the arcs are equal, if these two are equal, then the corresponding chords are equal. Is this understood? And so can we say that the angles subtended by the chord and by the arcs are going to be equal? The angles subtended by congruent chords at the center are equal. We can also say that the angles subtended by the congruent arcs at the center are going to be equal. I hope it is understood. Let's move on to the next property, which is exterior angle property. Now, we have studied exterior angle in our lower classes. We know that in a triangle, there are three angles in the interior of the triangle. And if you extend any one of its sides such that you are creating one more angle which has a common vertex and has a common arm. We have this as the common vertex and we have this as the common arm. If you see this, if you look at the angle, angle ACB and angle ACD, they have this as the common arm and C as the common vertex. Right? If this is the case, then we call angle ACD as the exterior angle. ACD as the exterior angle. Okay, and the angles definitely inside the circle, angle A, angle B and angle C are called as the interior angles. We have learned in 8th standard that measure of the exterior angle is sum of, either you call it as the opposite interior angles or you can call it as sum of the remote interior angles. Sum of the remote means which is far off, remote interior angle. Okay. Now, angle C is right next to D. It forms a linear pair. So, it is not far off. It is not remote. Then which are the remote interior angles? B and C, A and B. So, we'll say measure of angle ACD is nothing but measure angle CAB plus measure angle CBA. That means if this angle is 50 and this is 60, then can you tell me what will be the measure of this angle, the exterior angle? 50 plus 60, which will give me 110. This is a property that we've studied in our 8th standard, right? Now, moving ahead with this property, let us look at the next theorem, which is theorem number 9.8, a very important theorem, which reads, the angle subtended by an arc at the center. The angle subtended by an arc at the center of the circle is double the angle subtended by the same arc at any point on the remaining part of the circle. At any point on the remaining part of the circle. Let's look at a circle. Okay. Let's look at a circle and let's understand the statement again. What does the statement say? The angle subtended at the center. So let's mark the center. Let us mark the center as O. Okay, I've done a big center so that it's very clear. Let me call this as O. Angle subtended by an arc, let me consider an arc AB or whatever you want to call it. Okay, we are considering the arc AB. For ease of understanding, let me color it. Let me make it bold for you. Okay, now the theorem states angle subtended by the arc at the center. Arc AB subtends angle AOB at the center. This angle is double the angle subtended by the same arc AB at any point on the remaining arc. Remaining part of the circle means other than arc AB, anywhere you take a point, I'm taking it over here. Let me call this point as P. Then arc AB is also subtending angle APB, I'm sorry, APB at a point on the remaining part of the circle. The relation is what the theorem is trying to explain. The angle that is subtended at the center is double the angle subtended by the same arc at any point on the circle. That means if this angle is x, the central angle is 2x. Measure of the angle or the angle subtended by the arc AB at the center of the circle is double the angle subtended by the same arc at any point on the circle. Is the meaning of the statement understood? Now let's understand what is given to us then. Basically, we are given what is given to us? We are given a circle. In circle with center O and radius OA. What do we know? Arc AB, or to be more precise, we can say minor arc AB. Minor arc AB subtends angle AOB at the center of the circle. And angle APB at a point on the circle. What we want to prove? We want to prove that angle AOB is twice or is double the angle APB. To prove this, we are going to do a construction. We'll do a construction. We'll construct a ray. We will construct a ray. Excuse me, children. Okay. I'm sorry. We construct ray OQ. Ray PQ passing through O. We construct ray PQ passing through O. Now, what does this ray do? It divides the triangle. It divides the angle AOB as AOQ and BOQ. At the same time, we get triangle AOP and triangle BOP. Now, if we apply exterior angle, that means I'm going to look at triangles turn by turn. We have triangle AOP. At first, we're going to look at this. In this triangle, if I see, then what do we see? We see that this is the center of the circle O. This is point Q, P, A. Can we say that AOQ is the exterior angle? Right? It's like this. And we are saying this is the exterior angle. AOP. AOP is the triangle that we are looking at. And we are saying this is the exterior angle. I hope it is understood. Okay. So, the other thing that we notice over here is AO is equals to OP. Why? Radius of the same circle, children. Therefore, because in triangle AOP, AO is equal to OP, it becomes isosceles triangle. And whenever we have isosceles triangle, the first thing that should come to your mind is the isosceles triangle property, where we'll say that these two angles are going to be equal. Which two angles? The base angles. Angle A and angle P are equal. Let me call them as x each. Correct? So let's write this first part. We'll write the construction. What is the construction given to construction that we made? We wrote construction. Draw ray PQ passing through O, passing through the center O of the circle. Correct? Center O of the circle. Then we did, what did we say? We looked at the triangle. Which triangle did we look at first? We said in triangle AOP. What did we notice? We said AO is equals to PO by radii of the same circle are equal. Radii of the same circle are equal. So what do we know? It becomes an isosceles triangle. So we'll get the base angles equal. Angle A is equal to angle P. Isosceles triangle property, children. And we have called this angle as X. Next thing that we write is angle AOQ is the exterior angle, isn't it? Is the exterior angle of triangle AOP. Therefore, measure angle AOQ will be what? Sum of the remote interior angles. We just now revised it. So we'll get is equal to angle A plus angle P, that which is x plus x, 2x. So let me write here 2x. Right? Similarly, we can do on the second part. Similarly, we'll write the second part. What are we going to write here? Which triangle are we taking now? In triangle POB. In triangle POB. What do we get? We'll get again OP is equal to OB. Why? Same radii of the same circle are equal. Now, in that case, because we are saying these two sides are equal, it is an isosceles triangle and the base angles are going to be equal, children. P is equal to B this time. So we'll write here angle P is equals to angle B. Let me call it as Y. Angle P is equals to angle B and we've called it as Y. Again, we'll say what? Angle BOQ is the exterior angle. Is the exterior angle of triangle BOP. And therefore, BOQ is equals to angle B plus angle P, which is Y plus Y to Y. This is Y, Y, and this becomes 2Y. I hope you have understood this part. Now, let's look further. Okay. Let's look at the third part of the proof. We'll say consider angle AOB. If you look into the figure, we know angle AOB is what? Angle AOQ plus angle BOQ. And we just now proved that AOQ is 2x, BOQ is 2y. From here, we have 2 coming out common. We have x plus y. What is x? What is x? X is angle P, A and P, but we'll be needing P. P means APO and Y is BPO, right? From the figure, we can make that out. So I'll write here angle APO plus angle BPO. Now, if we look at it, what is APO plus BPO? Look at the figure, children. APO, BPO will give me this entire angle, APB, which is 2 times angle APB. And this is same as writing that angle at the center of the circle AOB is double angle of APB. Right? Hence the theorem. But children, this is just one of the case. Understand this little further. Let's discuss this. I hope you all have understood the proof. Let me rediscuss it with you. Okay, I hope you have understood. Go repeat it again and watch it. Let me show you. This is just one of the case of this theorem. Okay, What are the other cases then? For that, let us take three cases. Okay, children, let's take three cases now. Please understand this well. Okay. We are talking about the arcs. Center of the circle O, center of the circle O, and center of the circle O. First, we took the arc AB as a minor arc. The theorem we did, we wrote angle AOB is twice angle APB. We just now did it. In the second case, I'm going to select my arc to be a semicircular arc. Means in case 1, the measure of the arc is less than 180. So it is a minor arc. What kind of arc it is? It is a minor arc. Second case, I'm taking arc equal to 180. Measure of the arc is equal to 180. That means I'm taking a semicircular arc. Semicircular arc. And in the third case, I'm going to take a major arc. Now, when will the arc become major? We've already discussed all this. The major arc is always going to have measure which is more than the semicircle, more than 180. So then we are going to take major arc. We have understood the theorem for a minor arc. And on the same lines, we can prove this theorem for semicircular arc and major arc. Let's quickly rewind. We did a construction OQ. We said OA is equals to OP, radii of the same circle. So we got these two angles equal. We called it as XX. We said that AOQ is the exterior angle. Measure of the exterior angle is sum of the remote interior. So x plus x 2x. Then we said that OP is equals to OB, radii of the same circle again. So these two angles equal by isosceles triangle property. And then again BOQ is the exterior angle. We got 2y. And we said 2x plus 2y, 2 comes out common, x plus y, and hence we proved it. The same I'm going to prove over here. I'll take the semicircular arc. So this semicircular arc, children, let me just shade it so that it's very evident for you to understand. Okay, when we are talking about semicircle, means we are talking about this arc. So this arc is subtending this angle at the center and angle APB at any point on the circle. Nothing to do. We'll follow the same rule. Construction OP, OQ passing through P. Which triangle? AOP. We'll look at triangle AOP. We'll say that AO is equals to OP. Radii of the same circle, so these two angles equal. Let me call this as XX. In this case, this is the exterior angle. So we are going to have measure of the exterior angle, sum of the remote interior angles 2x. Again, we'll say that OP is equals to OB, radii of the same circle. So these two angles are equal. Angle P is equal to angle B, isosceles triangle property. Let me call them Y. Then we say that BOQ is the exterior angle. So it will be sum of the remote interior angles 2y. And then the last part remains the same, children. 2x plus 2y, 2 comes out common, x plus y. And we get 2 times AOB is 2 times x plus y. That is APB. Again, this time we are looking at a major arc. You look at the last part of the theorem that we proved above, you will get the understanding of it. It is exactly the same. The only thing that I want you to be clear with is it is not necessary that it is true only for minor arc. It is true for all kinds of arcs. We know there are three kinds of arcs: minor arc, semicircular arc, and major arc. Now, if I look at the major arc, then the angle subtended at the center of the circle is reflex angle AOB. I'll have to call this reflex because it is more than 180. Point P lies here, AO. APB is the angle subtended by the major arc AB at point P on the circle. We follow the same, extend it to Q. Now what do we know? We know that AO is equals to OP, radii of the same circle. Hence these two angles equal XX. Hence this angle, which is the exterior angle AOQ, will become 2x. No difference. We know that OP is equals to OB, radii of the same circle. So we'll get these two angles equal. Which two angles? P and B. Y. This is the exterior angle. So again, measure of the exterior angle 2y. It's exactly same three cases. So no major difference, right? So it is true for all the three cases. Now, one application of this theorem. Okay. I hope you all have understood the theorem, children. I'm going to one more application of the theorem, that if we have a circle like this, and if we have a diameter, diameter is a chord passing through the center. What is the measure of the arc in this case? What will be the measure of this angle? We know it is semicircle. Measure of a circle is 360. So measure of a semicircular arc will be half of 360, which is 180. So measure of the angle at the center is also 180. Okay. What about angle APB? APB is an angle subtended by the semicircular arc at point, say let's call this as point P only. Okay. We know by theorem, we'll know that the angle subtended by the semicircular arc AB at the center O is double. Angle AOB is double the angle subtended by the same arc at point on the circle, is double of APB. Now AOB we know is 180, is 2 times APB. So we'll get angle APB is 180 upon 2. Hence angle APB is 90. We know the property that diameter subtends a right angle at any point on the circle. At any point on the circle. You take the point anywhere. Say if I take a point here, then still this angle is going to be 90. If I take a point here, still it is going to be 90. What about if I go in the second half? If AB, if this arc is is semicircle, the arc APB is also a semicircle, no? So that will also subtend a right angle at any point on the circle. Am I understood? Is the theorem understood, children? I hope you have understood. Please write and practice. That is going to help you. By looking at the things and just watching the video is not going to help. Write it, practice it, and then you'll understand it better. Better and for longer time.